So welcome to the verification session. So we will start with Sasha, who will tell us about verifying Rust.
Hello. I have to admit, after Leo's keynote and before such an impressive session, I have a lot of pressure, but I'll do my best. Hi, so I'm Sasha. I work at Imperial College. I'm very excited to be here to present that work that's been going on for a long time. This is work in collaboration with Xavier, Denis, Petar, Maksimović, and Philippa, Gardner. In here, I present a new or somewhat new approach to verifying Rust, which we call hybrid. And I'm going to give you context first, which is that we're in an era where people are changing the way they write code. Normal developers, not PL people, are changing the way they write code. They used to write, C or whatever, or Python. And now they write type-check Python, or type-check JavaScript, or Rust, which is somewhat better than type-check C. And how long have we been waiting for this to happen? We've been waiting quite a long time. And even better than that, what we can say is that these languages have solved the problem of program correctness. Thank you for listening to my talk. Okay, maybe not. But for sure, these languages have made it much simpler to write correct code. And what we're going to argue here, and I don't think for a lot of the people I can see here in the audience, that's not news. But these languages also have made it easier to verify code. So this work and this talk is about hybrid verification. The goal is to leverage the nice parts of Rust while still verifying the less nice parts, and then we can do both more efficiently because of the nice parts. So I'm going to go into the what, the why, and the how in order. But this is a high-level talk. I'm not going to go into technical details. If you want more details, please go and read the paper. So this is a Rust code base. And all the green here is safe code. And the red here is unsafe code. And there's not so much unsafe code. But the goal of hybrid verification is to separate the work between safe Rust verification and unsafe Rust verification. For the safe Rust verification, we use Creusot, mainly because Xavier is an author of the paper, but also because we have the meta theory to support it. And then what we do is that we have a layer of abstraction in between. In Rust, it's usually just saying the function is safe, but for verification, we have a hybrid specification at the boundary between safe and unsafe. And the goal is that the tool that verifies unsafe code and the tool that verifies safe code should both understand this hybrid specification. So because there was no tool at the time for unsafe Rust verification, we started developing Gillian-Rust. There's now a few other tools, including Refine Rust, but I believe that still none of the existing tools quite satisfy this constraint that they can interpret specifications used in a safe tool. So that's the what. Let's talk about the why, and to talk about the why, we first need to talk about safe Rust verification, which is not quite the theme of the paper, but we need to go through that. So take this function here. It's quite simple, but really if you wanted to verify this, it's a lot of work because this receives a mutable reference to a vector, and it also receives a function, so it's a higher order function. It receives another function as a parameter. That function is an FN mute, meaning it can modify its environment. If it captures, it's a closure, so if it captures something in the environment, it can modify it. It also receives the mutable reference to a U32. And at the end, we check this. So it's very simple. It takes a snapshot of the first element of the vector. It modifies the second element of the vector, and it checks that the first element hasn't changed. This is automatic in most of the safe Rust verifiers. If it's not fully automatic, it's because some features are not supported, but in principle, it's mostly automatic. Safe Rust, and if you want more, you can add annotations for more functional correctness properties. The history of safe Rust verification started with Prusty from Peter Muller's group, mainly by Vaitotas. And they realized that you could basically automatically encode in separation logic the proof done by the borrow checker to get to a high level. And that would mostly automate a lot of the proof work done by that you need to do. Then RustHorn and RustHornBelt and Crusoe, they figured out you can have just a pure first-order logic encoding, just removing the separation logic entirely. Then Eneas, that you've heard about from Leo's keynote earlier, realized you can have a actually pure executable encoding of safe Rust programs. And finally, Flux is a more lightweight approach in liquid type. So they don't have all the same expressivity and so on and same automations, but more or less they capture this idea that having safe Rust, you can much simplify the proofs. Now, does anybody here do C verification? And can you try and imagine what it would take to verify the same code in C? Just first of all, it's higher order. There's not that many tools that can verify this. I mean, take real C code and verify it. That's not going to be easy. And it's going to be even harder because actually this does not hold. Because this modify function could be doing unrestricted pointer arithmetics, and it could go back in the vector and modify the first element. So it just does not hold in the first place. So what this says is that when Rust users, normal developers, write function signatures, what they actually do is they write separation logic specifications. That's not a new insight. That's from Ralph's work on RustBelt. But what this says is that in this new era, people change the way they write code, and for you, they write some specifications, some separation logic specifications. Can you believe that? The catch is they do it at a cost. They will only do it if sometimes they can say, I don't want to do it. So, all these languages have an unsafe counterpart, and in unsafe Rust, you can just write Rust that doesn't have all the safeguards as usual. And there's a catch also, because in the code I showed earlier, one of the things I do is take a mutable reference to the second element of the vector, and that is what we call internally unsafe. So in apparent, it's safe, but the implementation of that operation is implemented using unsafe code. So that's annoying, because if you get this wrong, then you could break basically all the type system properties given to you by the language. That breaks basically everything you've proven about the safe code. It's quite hard to verify. I'm not going to go into details, but this function here returns a mutable reference. So it returns kind of a promise that whatever you do with that mutable reference, you're never, ever going to break the invariant of the vector itself. But the good thing is that there's only 2% of the code or around that's unsafe, and it's all behind what we call safe encapsulation. So there's this boundary between safe and unsafe code, and supposedly if you check at the boundary, then you're fine. Hence hybrid verification. The goal is, if instead of putting a lot of effort on the entire code base, you put a small amount of effort on the safe code and a lot of effort on the unsafe code. And that includes, I don't know, I showed a simple example, but tools like Crusoe can verify higher order iterator function doing crazy stuff, and they will do it with little help compared to what you would need in something like C. Taking a breath. We've seen the what, we've seen the why. Let's talk about the how. So we've put these two tools together, Gillian-Rust and Crusoe, and then a bunch of meta theory that people who are much more clever than me did. And specifically, we use Crusoe because there was meta theory to back up the soundness of Crusoe using separation logic and connecting it to RustBelt. And then we built this new thing based on Gillian. So I'm going to give a very, very quick introduction to Gillian. Gillian is what we call compositional symbolic execution. There's other tools that do similar things. Viper, CN, Xavier, very fast before that. The specificity of Gillian is that it's parametric, meaning when you want to create a new tool based on Gillian, you kind of explain to the tool, you implement symbolic actions and core predicates, which form the basic operations of your state and the basic block of the separation logic you want to use. We've instantiated it for these languages, but interestingly for Rust, the kind of new, kind of exotic state updates we get are, for example, allocating lifetimes, and the new kind of core predicates we get are, for example, lifetime tokens or prophecy observations or things like this. So Gillian-Rust is a lot of new things that are described in the paper. I'm not going to go into details into everything, but we have a new kind of symbolic heap model to automate heap operations that includes normal Rust stuff, but also when you need to do pointer arithmetics, it will kind of try and automate that specifically for array reasoning, vectors, and all that. We encode the lifetime logic, and we importantly bring new automations that are specific to how CSE, compositional system execution, operates. We have encoding and automation of some prophecy reasoning. And also, the most important part for me is this front end that takes Creusot specifications and compiles them to separation logic specifications. And the way it works, and what makes everything work, is that Creusot, for example, when you talk about a vector, when you talk about a linked list, it can only see an abstraction of it. Creusot, when you talk about a vector, you say, I push at the end of a vector. Before that, I have some sequence of data. And after that, I have some sequence of data with an element at the end. And that allows you to reason very efficiently at the abstraction level. And Y3, on which Creusot is based, can reason very efficiently about this. Unfortunately, if you want to reason about unsafe Rust and you want to reason about the implementation of the vector or the implementation of a linked list, then you actually do need to think about the pointers and the separation logic that's there. So Gillian-Rust has that view, can reason at that level. And what works is this interface where you can convert from one level of abstraction to the other. Again, that's not really a new insight. That was RustBelt and RustHornBelt, mostly RustHornBelt for that one. But what's new here is that we actually have two tools that are able to think at those two level abstractions and work together. And this is really what makes hybrid verification real. I don't know how long I've taken, a bit in advance, but I'll still talk about the last ingredient, which is targeted automations for unsafe Rust verification. And this is made possible by two things. First of all, we have Gillian. And in Gillian, we can encode these automations. And second, we have hybrid verification, which means most tools, if you have to think 99% of the time about safe Rust and 1% of the time about unsafe Rust, then probably the unsafe Rust automations are not going to be very good. But here, because we have hybrid automation, because we split the work, we can let Creusot think about how to automate safe Rust verification, and we can think about unsafe Rust verification. And we can make those automations work for the cases we know happen. There's rarely any very higher order function happening in unsafe. There's some, but most of it is just manipulating a bit of pointers around, and we need to do that efficiently and mostly automatically. So for example, this is the real code from the standard library of what vec_push is. So it's just adding an element at the end of a vector. This is the real Creusot specification of vec_push. It's missing a precondition about the length of the vector because you don't want to overflow your integers and so on, but it's not very important. And to verify this, almost automatically, Gillian does a lot of things for you. First of all, there's this notion of opening and closing borrows. So you need to think about the invariant behind your mutable reference. And you need to open that invariant and close that invariant. We've designed new automations to do that. And so Gillian can do it fully automatically. And if it cannot, you can still ask to do it manually. But most of the time, it will do it automatically. In Gillian, if you don't have a specification for a function, you don't need to specify it. Most of the internal grungy functions like razor for push don't have really a nice specification. You can specify them, but it would be difficult and painful. Here, we'll just symbolically execute it in all cases that we encounter. And if it works, and it's still sound. We have pointer arithmetics. As I said, our symbolic heap model can automate a lot of the reasoning about arrays. And here, you add an element. It might have reallocated and so on. It's a bit grungy, but really, it's not that difficult to automate because really it's not that hard. It's just a lot of cases, so you need something that goes fast. And here, Gillian-Rust is not fully able to conclude the proof. You need to tell it to there's a prophecy variable going on. You need to say something about what happens when the lifetime ends. And here we have one line of annotation for the whole proof, asking Gillian-Rust to resolve that prophecy and assert that you're done with the mutable reference. Once that proof is checked, then you never have to think about it again from the Creusot point of view. You know that push is just something that takes a sequence of data and adds something at the end. What we're pretty proud of is that this takes less than 3 seconds to verify. This is some orders of magnitude faster than things that have been done before, with a lot of trade-offs, obviously. And so, wow, this is amazing. We have many, many limitations. I'm not going to list all of them. We probably have more that we haven't thought about. We haven't used the tool to a huge extent, but for what we've used it so far, it worked pretty well. I think what I want to say from this slide, which is a pre-takeaway, is that Gillian-Rust isn't really a production-ready tool. I'm not telling you if you use it tomorrow in your company, you can instantly verify all your code base, and then you get all the guarantees of Crusoe also after that. It would be great if we were at this stage, but it's not ready yet. It's a prototype. What we wanted to do is show the feasibility of this hybrid approach, and we managed to do that. So for me, hybrid verification is the real takeaway of the work. Now, I see my PhD supervisor looking at me like, why are you saying this? Here's a post-pre-takeaway. We did pretty good. We did have new automations. We did prove new things from the standard library. And for the things that were already proven by other people, we went a few orders of magnitude faster. So, and with less automations. So we did pretty good. There is a trade-off, of course. We're not foundational. We rely on CD solvers. We rely on Gillian. But overall, it's a pretty good tool. And if development continues, I think it can be quite impactful. So after the pre-takeaway and the post-pre-takeaway, we can move on to the takeaway. The takeaways are hybrid verification is good. Yes, hybrid verification is good. 98% is, I would say, boring on the separation logic level. You want to do the boring thing and verify really the properties you care about. And for that, you want to use a safe Rust verifier. And for the 2% of unsafe code, you really want those automations and those tail automations. And this is what hybrid verification gives you. Thank you very much.
Okay, we have time for maybe 1 or 2 quick questions.
Hi. So I noticed that one thing you probably didn't mention, but one thing I noticed, you've actually verified get unchecked mute. So is it correct to understand that you extended Crusoe to also support specs for unsafe functions?
Not Crusoe directly, but Gillian-Rust verifies the specification used by Crusoe. So in a sense, we provide the guarantees that Crusoe needs for unsafe code, yes.
Okay, thank you.
Cool talk. I'm wondering how you think this compares to something like Varus that allows you also to mix safe and unsafe with ghost linear types and so on.
So yeah, so Varus is one of the coolest tools out there. Currently, at least, Varus has a proof-oriented programming approach. So if you want to verify a linked list, you kind of need to implement it using the Varus primitives or using the Varus standard library. So even though Varus has made progress trying to actually verify things from the real standard library of Rust, I don't think, last time I asked Andrea, he confirmed that currently Varus wouldn't be able to verify what we verified in the standard library. But it's just, for me, a different approach. And if everybody could do proof-oriented programming, I would be much happier in my life. But I think Varus is really cool. It's just different targets.
Okay, so let's thank the speaker again.